Rashid, can you close your eyes? Can you guess what is in the basket?
I think it is sweet.
Yes, it is. Do you know how to find the probability with these sweets?
Yes, let's find it together.
So, I will start with the introduction. For this project, we will base on probability, which is the study of how likely an event is to occur. Probability helps us understand and measure uncertainty in real-life situations, such as choosing a sweet from a mixed packet where the outcome is unpredictable. In this project, we explore the differences between the theoretical probability and experimental probability using three flavors of sweets, which is coffee, caramel, and chocolate mint. Theoretical probability is calculated based on what we expect to happen, assuming every flavor has an equal chance of being chosen. On the other hand, experimental probability comes from actual observation, which is counting how many times each flavor is selected during the experiment. By comparing these two types of probability, we can see whether our real-life results match what theory predicts. This helps us understand how randomness, uneven mixing, and natural variation can affect outcomes. This is the objective of the study. The first objective is to find out the frequency of each flavor of the sweet, which includes coffee, caramel, and chocolate mint. The second objective is to understand the difference between experimental and theoretical probability. The third objective is to calculate mathematical expectations involving mean and variance. For the methodology of this experiment, the process begins with preparing 30 sweets of three different flavors, which include 40 coffee flavor, 10 chocolate mint flavor, and 6 caramel flavor. All 30 sweets are then placed into a container and shaken to ensure that the flavors are properly mixed. After that, a hand is inserted into the container to randomly select one sweet, and the flavor obtained is immediately recorded. The sweet is returned to the container to maintain the condition of replacement. The container is shaken again to remix the sweets, and steps of selecting, recording, and replacing are repeated until a total of 30 trials are complete. Finally, all outcomes from the 30 selections are compiled and documented in a table for analysis. Before the experiment, each flavor had a different total amount. Coffee had 14 sweets, chocolate mint had 10, and caramel had 6. After we carried out 30 random draw with replacement, we recorded the frequency. Coffee was drawn 40 times, chocolate mint 30 times, and caramel only 3 times. Even though all three flavors were supposed to have an equal chance of being picked, the results were still different. This shows that random sampling doesn't always produce equal frequency, especially when the sample size is small. For the result of the theoretical probability, we assume that every sweet in the packet has an equal chance of being picked. Based on the total number of sweets, we calculate the probability of each flavor. So for the coffee, it has a theoretical probability of 14 out of 30. So for the caramel, it has a theoretical probability of 6 out of 30. For the chocolate mint, it has a theoretical probability of 10 out of 30. This value represents what we expect to happen before doing the experiment.
For question number 3, what is the experimental probability of obtaining each of the flavors? Experimental probability equal number of times the event happened, divide total number of trials. This experimental probability is found by taking how many times each flavor was picked out of the total 30 trials. So the results are coffee is 14 over 30, caramel is 3 over 30, and chocolate mint is 13 over 30. This fraction represents the experimental probability for each flavor in our experiment.
For this question, the experimental probability that the selected sweets are not caramel is obtained by using the complement rule. Since the probability of an event and its complement must add up to 1, the probability of not caramel is calculated as 1 minus the probability of caramel. The experimental result shows that caramel appears 3 over 10, so the complement is found by taking 1 minus 3 over 10, which is 7 over 10, and it simplifies to 9 over 10. Therefore, the experimental probability that the selected sweets are not caramel is 9 over 10. For this question, we want to find the theoretical probability that the selected sweet is not caramel. To do this, we use the complement rule. P bracket not caramel equal to 1 minus P caramel. Since the probability of caramel is 6 out of 30, we subtract it from 1. This gives us 24 out of 30, which simplifies to 7 over 10. So, the theoretical probability of picking a sweet that is not caramel is 7 over 10.
For question C, explain why experimental result may not exactly match theory. The result is not match theory because of random change, small sample size, and human error. For discussion, question 1, are the results close to the theoretical probability? The results are not exactly the same as the theoretical probability. In real-life experiment, small differences are normal because the selection are done randomly. Question 2. Why might there be difference? First, because of random change. When we pick a sweet blindly, every sweet has the same probability, but the actual outcome can still vary each time. This natural variation is completely normal in random process. Second, the sample size is small. We only pick 30 sweets, so the result can fluctuate more. With a small number of trials, the observed frequencies will not always match the theoretical ratios. That there are human factors. First, the sweet may not have been mixed properly, so some stay on top or at the bottom. Second, students might accidentally feel the texture of certain sweets even with their eye closed. Third, someone might forget to put the sweet back into the bag, which breaks the with replacement rule. Four, there may be recording error when writing down the result.
For part A, we are finding the probability that x is greater than 3 since the function is 1 over 7 multiplied x plus 1 ds. For the range from 3 to 4, we set up the integral from 3 to 4. When we integrate x plus 1, we get x squared over 2 plus x. So I just substitute the upper limit, which is 4, and the lower limit, which is 3. After simplifying, the difference gives us 9. Then we multiply by the constant 1 over 7. So the final probability becomes 9 over 14. This means the change that x is more than 3 is 9 over 14, which is more than half. For part B, we want the probability that x is between 1.5 and 3.5, but the function is different on both sides of x equal to 3. So we need to split the calculation into two intervals. From 1.5 to 3, the function is 1 over 7 dx. When we integrate 1 over 7 dx, we get 1 over 7x. So I just substitute the upper limit, which is 3, and the lower limit is 1.5. After substituting the value, that part gives 3 over 14. Then from 3 to 3.5, the function is 1 over 7 multiplied x plus 1 dx. So I integrate that and substitute the limit 3 to 3.5. After simplifying, the second part gives 70 over 56. Finally, we add both results together because it is a continuous probability over two connected intervals. So 3 over 14 plus 70 over 56 is equal to 29 over 56. To find the mean, use the standard formula. ds is for integral f fs dx. Since the density function is defined in two different intervals, split the calculation into integrals. The first integral covers the range where the density is s over 3, and the second integral covers the part where the density is 1 over 3 s plus 1. Then integrate each part separately, substitute the upper and lower limits, and combine the result. After simplifying all the terms, the final value for the mean is ds equals 61 over 21. This represents the expected or average value of the distribution. Next, calculate the second moment using es squared equal integral x squared fs dx. Just like before, split the integrals according to the two pieces, expand the expression, integrate term by term, and evaluate the limits. After combining and simplifying everything, the final result for the second moment is es squared equals 1781 over 84. This is an important value because it helps us determine the variance. The variance measures how spread out the values of x are around the mean. Using the formula var x e times x squared minus es squared, substitute the two values we compute yearly. After performing the subtraction, the final variance is var x equal 1517 over 1764. So to conclude from the 30 cross that we did with replacement, we managed to achieve all the objectives of this experiment. Based on our result, the coffee flavor appeared the most with 14 drops, chocolate milk came close with 13, and caramel turned out to be the least, which is only 3 drops. These differences actually show us something important. Even if the theoretical probabilities are supposed to be equal, real-life random sampling can still give slightly different outcomes. Overall, our experimental probability is still close to the theoretical one. The small differences happen because of randomness and the fact that our sample size is only 30. Lastly, when we calculate the mean and variance, it helps us
understand the statistical expectation more clearly. It also shows how experimental data can reflect the actual distribution in a population.